Hello, welcome to another Midnight Maths video. In this one, we're going to be covering the tabular method, uh, aka integration by parts. Um, but the reason I wanted to make this video is I strongly prefer using this right here, the tabular method, over the vanilla formula, which is usually given like this, right? And it's just like a faster way to write exactly the same thing. So in this video, I'm gonna sort of develop the tabular method, like sort of informally prove it, and along the way, I'll show you how it works in abstract, and then in future videos, we'll sort of go over practice problems. So this is, of course, our vanilla IBP, regular IBP formula. So what we're going to do is usually when we're talking IVP, we're talking products. So this is just a general product of two functions and we are integrating it. And so what we're going to do is over the course of this video, we'll sort of expand this table. So it'll just be empty for now. Okay, so we're going to assign U is going to be F, okay, and then dv is going to be G, right? And now that I've made these choices, hopefully you can see why I'm gonna need to sort of define some functions here. So here I'm just saying the general antiderivative of G is gonna be G1, and since we're gonna use IVP more than once, I'm gonna need a G2, which is basically just the antiderivative of G1. Plus a constant, and the pattern continues. Now, of course, we don't actually need to worry about these intermediate constants for now, because they do cancel out. And then you have du, so f prime x dx, and then v is going to be g1, that's the new function we just defined here. So at this point, we can just apply the formula, right? So let's write this down. And what we're going to get is u is going to be f, and then v g1 minus integral v du. Okay, now the first pattern I want you guys to notice here is f has not been differentiated yet, but g has already been integrated one time. So why is that? Well, if we go back to the formula, right, we actually had to, so remember u was f and dv was g, and basically to get from dv to v, we integrated one time, right? So this was, we had to anti-differentiate one time. But then the u, we didn't leave, so the u was left alone. So that's what this is here. But then over here, we have a different story where both of them have been touched. So v, we had to integrate to get to v, and then we also differentiated u because there's actually an f prime inside du, right? So we can sort of neatly express this pattern with a table where we have this sort of lag. We represent this by putting f of x here, g over here, just like, because that's what we assigned u and dv to be. And then we differentiate it on the left column and integrate on the right column. So what ends up happening, so you integrate on the right column. So what you end up getting is you differentiate f, but you anti-differentiate g. I use the terms integrate and anti-differentiate interchangeably in this video. At this point, you go, okay, well, f and g1, that's actually just this. And so we're going to draw a line between these two functions. And if we ever draw a diagonal line between two functions, it means we're multiplying them. So we're multiplying f by g1. But then we are integrating g1 and f prime, which are these two. So we're going to draw a straight line. So when we draw a straight line, it means multiply, but then integrate. So I'll sort of draw this, right? So, but of course there's a minus sign here, so maybe because this pattern almost works. This seems pretty promising. Let's put a minus sign. Okay, actually, hey, why not? Let's make another chart. Let's make another sort of column, if you will, and we can put sign or something. And we have a minus sign here, so we minus and then integral of g1 f prime. And I guess over here, since it's implicitly positive, we'll just sort of put a plus here because we made it. Okay, so now at this point, we could just stop. A lot of IBP problems only require you to use one time, right? But the real advantages of this method really start to show when you do it multiple times, when you have to do IBP multiple times. So what we'll do is we'll use it again on this guy. So instead, we're going to have u, so u is f, so we're going to keep letting u be related to f prime this time, and then dv will be g1x dx. Sorry, I don't think I put that over here. Sorry. So what that ends up being is du is going to be f double prime x dx, and then v will be g2x. So at this point, we're just going to use the formula again. So I will just use the formula now. So it's going to be u v minus integral v du. By the way, do make sure you put your differentials when you're, especially when you're using this formula. At this point, so this right here, this quantity is actually just equal to this. So to generate an expression equal to the original integral, we have to include this part, right? Because we essentially just wrote an equivalent version. So what we're going to do is copy that minus part, and then we're minusing the whole thing, right? So all of this is all of that right there. So we can do some simplification. So we can say this is f g1 minus f prime g2 plus, so minus minus make plus, and then integral g2 f, I think the apostrophes were left behind. So f double prime x dx. And at this point, we have a similar pattern where f wasn't differentiated at all, so differentiated 0 times, but g was integrated 1 time. But then over here, f was differentiated once, and g was integrated twice. So we can, continue the table. So I'll move the table down, and this time we're going to have f double prime x over here, and then let's sort of clear this stuff. It's going to be g2, and we're gonna have a plus sign right here, because what's gonna happen is, so these two are the same, right? So this is the same as this fg1 is the same as before. This f prime g2. So what really happened here? What really happened here is we got a minus sign in the beginning when our table was just this, was just the top 2 rows. Remember, this was the minus sign that told us to add that one, right? But what ended up happening is it lingered. So it lingered over because we were still writing equivalent expressions to the original. But then this minus sign meant this guy. So now it made this product negative. But this product is now a diagonal. It used to be like the straight one on the bottom, but now you're diagonally multiplying. So really, all of these minus signs are the same thing, is what I'm trying to say. If you do need to pause and process that for a bit, feel free. But you sort of have this, and then now what happens is, how come this is a plus? Well, you have f prime g2, and now it's positive. Well, where did the positive come from? What happened? Well, it started with this minus sign, right? Which actually originated from the original formula, right? So it came from there, and then that minus sign lingered. We had another one come in. So this guy had another minus sign attached to it, and that came from the formula directly, right? It came, but then these two came together. These two came together, and formed a plus sign. So really, the whole reason we see this alternating pattern of plus minus plus is single-handedly uh, this minus sign in the whole IBP formula, because it sort of combines with other ones as you go along until you get minus plus, or plus minus plus, and so on. And you could actually do the third time on your own, and you would see you'd get a minus here. So let me sort of clear these annotations. And at this point, hopefully you can see that however long we continue this pattern, however long we want to keep writing the table, we're still going to get equivalent expressions to, remember, we're looking at this, as long as we do follow these rules, right? Where every time, so we have a U column, a DV column. In this column, we differentiate repeatedly. In this column, we integrate or anti-differentiate repeatedly. And then we have a sign column that starts with plus and then alternates down the bottom. And then what we do is you draw lines diagonally and multiply the functions while considering the sign. So this would be plus f of x times g1, but this would be minus, this would be minus f prime g2, right? That's not a minus sign. This would be minus f prime g2. And then afterward, once you get to the bottom, sorry, let me clear this line. Once you get to the bottom, you integrate at the bottom. So just like we did in the first table, we integrate at the bottom. So this is really the manifestation of the du. This part is coming in at the very bottom. And these top ones are just sort of UVs, right? They're the UVs in previous iterations of IBP, right? So you integrate at the bottom, and then you also have to consider the sign when you're doing that. And, with this table, the idea is with this table, you can quickly write down an IBP expression depending on whether you want to use it once or twice or even 3 times, or you could go on more times. So that's it for the derivation. Now, at this point, you might just be convinced that this method is actually more complicated, but in another video, I will show you how this tabular method, once you get used to the little sort of rules here, then it becomes pretty easy and definitely a lot less writing than the original formula. So until then, I will see you guys in the next one.